live. We're live. Okay, so again, we're going to do mirrors today, and lenses tomorrow. And basically, ray diagramming is pretty cool. There's something called a lens equation and a mirror equation that allows you to determine where an image is based on a mirror and its curvature. And then you can use art to check your work. So first of all, we have three types of mirrors. A flat mirror. There we go. One of the things that's critical to understand is when you see these rays, these are called rays, you are looking at the universe illuminating the object. Okay? So the universe is illuminating the object, and then the light hits a flat mirror. And what does the law of reflection tell you is going to happen to those rays? They're going to go right back because they're currently sitting at 0 degrees to the normal, 0 degrees to the normal, 0 degrees to the normal. So they're going to get reflected right back. But you know that when you see an image in a flat mirror, it looks like you're behind the mirror, right? So the light actually comes back this way, but your brain puts the image behind the mirror. So since the image is not where the light is, we call this a virtual image. It is created by light that is not there, okay? Because light hits the mirror and bounces back. But you know, you're like, hey, there's someone in that mirror. When you see the mirror, you're behind the mirror. So it's a virtual image. Two types of images, virtual and real. Real images are formed by real rays where the light is. Virtual images are formed with virtual rays. That's not where the light is. Is that clear? If it doesn't, you'll become more. Okay, so then a concave mirror is one that's caving towards you. So this is a concave mirror. Ooh, concave mirror. Yeah. You're like, whoa, 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 whoa. Yeah, concave mirror. It's really dirty. Oh, well. Things exploding in my chemistry lab. I need to clean these things. But this is a concave mirror. And a concave mirror, and concave anything, is something that curves towards you. Okay? Like, think of like you're walking into the cave, a mouth of a cave. The mouth of the cave goes around you. So concave is caving in on you. Caving in on you. And again, it's not just mirrors. Everything that has that shape is concave. A spoon is concave on one side, and then convex on the other side. To vex someone is to make them angry. So when you're vexed, you're like, get away from me. Get away from me. So convex is moving away from you. If you're in a valley is concave. If you're on a hill is convex. Make sense? And the reason that it's important to remember is on assessments, it won't actually give you a device. It won't draw you a device. It'll say the object is this far from a concave mirror. And you know how it behaves. Okay, so here's our concave mirror. Light is going to illuminate our object. Light is going to strike the object. And then the law of reflection kicks in. Actually, white. Yeah, this is white. Okay, so there's the normal there, and there's the normal there. So this is going to come right back because it's at 90 degrees. But on the curvature, this one's going to do the law of reflection here and the law of reflection. Well, I messed that one up. Let's try this again. So there's the normal and there's the ray. Get the idea? Yeah. So since the law of reflection applies even to curved mirrors, the rays that come back are going to be curved towards the middle. Now, since this is where the light is, this is a real image. What you see in a concave mirror is a real image. And whether it's upright or inverted depends on when you view it beyond the focal point or inside the focal point. In this case, she's viewing her hand inside the focal point, so it's upright. And in this case, he's viewing himself outside the focal point, so he is inverted. So, an image can be real or virtual. It can be inverted or upright. You guys should also be seeing an inverted image.
Yeah.
Because you're really far away.
Yep.
My first introduction to these mirrors
Okay.
was at Green Valley High School at
Upside
a
down.
physics and EP workshop. And I took the mirrors downstairs and I started just cooking stuff with it. It was like early mid-July. So I was just taking the lens and like, let's go fry something. And you can totally do this. Not with these, but you can buy your own. Then you can go outside and get the sun and then hold a piece of paper and it'll ignite it right away. It's awesome. But not these,
What?
because these are my gun.
Yeah.
Okay? So, virtual, real. Real if it's where the light is, virtual if it's not. Upright if it's matching the object and orientation. Inverted if it's upside down.
Can you go over why the first one's virtual and the second one's real?
Yes, because we know light bounces off a mirror.
Yeah.
Light reflects off a mirror, but it would reflect right back to you. So you put the object back here, which means it is made virtually with light that is not there. The viewer is reconstructing the image, and it's reconstructing the image. It would make sense. It wouldn't make any sense if it's right here, like right where you are. You wouldn't be able to see anything. So you recreate the image back here by putting those rays together. So we use dashed lines to represent virtual rays.
Yeah.
So a virtual ray is made by virtual rays. This is a real image because the light bounces off and recollects right here.
Okay.
So far, so good?
Yeah.
Okay. Now, this is kind of interesting. Convex mirrors, they vex you, they vex away from you. The great thing about convex mirrors, you can put them at the corner of Walmart and you can see around corners. But everything in a convex mirror is teeny tiny because it collects a lot of information and focuses it on a small point. Do convex mirrors make real or virtual images?
Virtual.
Yeah, they can only make virtual images. You can kind of see that when the light leaves the object and hits, it's going to get what's called dispersed, diverged. There we go. So the light is going to be diverged. Here, the light has converged. Here, the light has diverged. So does that mean a convex mirror doesn't make an image? Makes a virtual image. So you can basically track the rays back, and a convex mirror will make a virtual image.
So it's just whether the rays actually reconnect, like all joined together. Okay.
Yep. So far, so good?
Is that why?
Yeah.
My head on this one, all like weird moves.
Okay, so we have three words of 6. When you are describing an image, you always use these 3 words of 6. It's either virtual or real. It's either upright or inverted, and then it's either reduced or magnified. So here, it is neither reduced or magnified, but it is virtual and it is upright. Here, it's reduced and real and inverted, and here, it's reduced and virtual and upright. Huh? Okay. If you're comfortable so far, give me a thumbs up. Moving right along. Okay. In front, behind. Oh, we're going to basically take this simple design and add a layer of complexity to it. But if you ever hear the word principal axis, that's the thing that runs perpendicular to the plane of the device. So if the device is vertical, the principal axis is going to be horizontal. See anything else? Nope. Okay. And the point at which the rays converge, either on the real side or the virtual side, is called the focal point, usually given the letter F. Okay? Additionally, when we're doing these, because of the way the math works, we usually use centimeters or millimeters. We very rarely need to use meters because, well, just as long as we use the same units. So we usually use centimeters and millimeters. Okay, this is the mirror equation. F is the focal length of the device. In this case, if I remember correctly, the focal length is right about here. So from the plane of the mirror to here, that would probably be about 35 centimeters. So if you go outside and put a piece of paper here, it'll go, just burst into flames. Well, not burst, but it'll catch fire. Okay. So F is the focal distance. DO is the distance of the object from the plane of the device. DI is the distance of the image from the plane of the device. And with a mirror, the focal distance is half the radius of curvature. And I do not know why they show it that way.
That's kind of.
Yeah, it's really good. I don't know why they show it this way, but if you realize you can just do F, 2F, R, so R equals 2F. So the radius of curvature is the radius of curvature is twice the focal length, or the focal length is half the radius of curvature. I don't know why they show it this way. Again, this is what's left over from textbooks. Okay, objects will have positive values. Objects are always real. If your image is real, it will also be a positive value. If your image is virtual, it will be a negative value. Okay, so DO is always positive no matter what. DI is positive if it's a real image and negative if it's a virtual image. What about F? This has a focal distance right here. So its F would be positive. You see where the rays converge? Imagine the rays come in and they converge to this point. On the other hand, a convex mirror has a focal point over here because the rays diverge and the virtual rays converge here. So the focal point of a convex mirror is negative. Are you with me so far?
Yeah.
So, in summary, if something is real, it has a positive value. If something is virtual, it has a negative value. Distance of object is always real because objects are always real no matter what. No matter what kind of device, where they are, DO is always positive. All right, be really careful with these reciprocals. And always check your work. Again, that's what the art comes in. So we can do our math and we can figure out, you'll be given 2 of these, and you're gonna figure out where the third is. Then we basically do the arts and crafts to check our work. It happens a lot. Like, oh, I forgot to divide, forgot to take a reciprocal. Oh, I made the virtual thing positive instead of negative. Happens a lot. And then, of course, magnification is simply a ratio of the height of an image to the height of an object. And one of the great things about that is because of the way math works, it's also the negative ratio of the distance of the image to the distance of the object. This will reveal itself when we practice. So when you get magnification, a positive magnification is measured above the principal axis. A negative magnification is measured below the principal axis. It's inverted. A magnification of larger than 1 has an image that's bigger than the object. And a magnification less than 1 has an image that's smaller than the object. Those are all the rules. I did post this on Canvas, right? This. Okay, check and make sure I did because that's actually important. Okay, so let's label a few of these. Here's our object. Here's our image. This is a what mirror? Concave, which means the F is going to be positive or negative? Positive. Okay. Oh. So this is the distance of the object, always measured to the same point, perpendicular to basically perpendicular to the principal axis. The plane of the device is always perpendicular to the principal axis. So here's our DO. DO is going to be positive or negative? Positive. Here's our DI, distance of the image. DI is going to be positive or negative?
Positive.
Positive. And the F is also going to be positive. HO is measured from the principal axis to the top of the object. HI is measured from the principal axis to the top of the object. I showed them here. This is a different way of showing. I don't remember what it's called. It's not, maybe it's principal. No, it's not principal. It doesn't. This style has a different way of doing rays. I'm going to show you the way we do it today. It's much better than having basically the image and the object be anchored to the principal axis. Okay, so we would describe the image as real, that's where the light is, reduced has a magnification less than 1, and upright, it has a magnification that is positive. All right, how are we doing? All right. Oh, if you ever see this online, this is before we had computers that could do subscripts. The variables were P and Q, P for DO and Q for DI, and that stuck for 100 years. And then people said, you know, we can do subscripts in textbooks now. So they started moving to DO and DI. Thank goodness. But yeah, sometimes you still see P and Q out there, you know, bad teachers. Okay, so here's how the ray diagramming works. I'm going to give you this and we're going to do a couple together. The first ray that we draw runs parallel to the device and then through the focal point. If the focal point is not given, you draw it. You basically measure the center of curvature and then have it. That's the focal point. So the first ray goes parallel through the focal. That's one color. The second color runs through the focal point and then runs parallel. Pen number 2. Pen number 3 just goes through the center of curvature as a check. I know, like, why don't we just use that one? That's just the way it's not done. So first ray, parallel focal. Second ray, focal parallel. Check ray through the center of curvature. You ready to do some together?
Sure.
Again, I apologize if these run off the page. Every now and then, like this obviously this worksheet's 8 years old. I don't know what happened to my other practice worksheet, so I wonder who it could be. Howdy. Hold on. Okay. Oh, jeez. It's Cameron. Wants to see you. Probably wants to yell at you for something.
Now?
Okay, so you're gonna need a ruler.
My what?
It says, "May I see you, please?"
Oh.
So you're gonna need a ruler. You're gonna need your normal pen and pencil, and then 3 colors to make rays.
Okay.
And I do not have red, so I guess it's gonna be brown. So I'm gonna make my principal axis. You can make it as long or as short as you want. Now you have some like thin curves here, and that gives you the plane of the device. I'm going to draw myself a plane of the device. I don't know exactly what it is. And again, the device runs around the planet. It is not limited. The plane of the device is not limited by the actual device. In other words, if you need to bend a ray up here or way down here for this device, that is okay. The light does not have to strike the device because we are modeling. As far as light is concerned, that device has an infinite height. Is that clear? Okay. So what I need you to do right now is I need you to measure. You're going to use millimeters. I'm going to use centimeters. So you're going to use millimeters. Me, centimeters.
How much trouble are you in? What you want? Welcome back.
Okay.
So as I was telling the boys, the plane of the device has an infinite height. So you have your center, you have your principal axis, and you have your device. I'm just going to go ahead and make a line. What I need you to do now is measure this distance here from the device to the focal point. Oh, I always label this too, so I can keep track. This is a concave mirror.
20. First one?
Did you get 22?
What?
32.
Is it not the arrow?
No, the F first, then the arrow. So,
You guys tripping.
Okay, what?
okay,
I'm
so we're doing this one together.
Okay.
I'm gonna use centimeters, you're gonna use millimeters.
Okay.
So measure the distance from the focal point to
Okay.
the,
Gotcha.
the plane, the device plane.
22 millimeters.
22 millimeters. Okay, so F is 22 millimeters. So 22 millimeters, there is F.
Okay.
Next. Now we're gonna measure for DO. Measure from the device plane to the arrow.
Just flat, right?
Yes. Along the principal axis.
55.
55. And then measure HO, the height from the principal axis to the top of the arrow. 5. So hey, look at that, I ran out of principal axis.
Like 13.
13 millimeters?
Yeah.
DO, 13 millimeters. I'm gonna make mine 13 centimeters. 13, all right. So, zoop, 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 zoop. Okay, so there is my DO, there is my HO. Okay, we got all the important parts. Now we can start drawing our rays. Change color. My first ray is going to be blue. So R1, well, I don't have to draw it. R1's going to be blue. So you're going to take your first color, set it parallel to the principal axis, and draw a line. This is the light that is bouncing off the object by the universe. Next, where it strikes the device, have it go through the focal point.
Nice.
Oh, by the way, there's one other thing. If the F is 22, the C is 11 millimeters. We're going to need C as for our third ray. No, if the F is 22, the C is 44. It's double. C is 44 millimeters. That's the center curvature. All right. Are we good so far with first ray? Parallel focal? Next ray is the opposite. You're going to line it from the top of the object through the focal point until it strikes the device. Boop. And then it runs parallel. All right.
Oh, shoot.
That's why we're using pencils. I have an extra because Amy's not here. Try to, yeah.
That worked well.
Well, it's just brown now. It's okay.
All right. We're good.
Yeah.
Okay, so it clearly indicates that we have an image right there. So I'm going to go ahead and need a ruler because for small things I need a ruler. So we're going to draw our image. The image will be anchored to the principal axis, like so. And we're going to measure HI. And measure DI. I'm going to take my meter stick for that. 30. So HI and DI. Now our check ray goes to the center of curvature. So you line up from your object to the center of curvature, and if it hits, well, pretty close. If it hits your image, you did it right. The third ray is always a check. Sometimes we don't even draw it, so
A little off.
yeah, it's gonna be a little off, that's normal. Mainly because we're using a perpendicular lens or a perpendicular mirror and not a curved mirror. But that's okay. Always gonna be a little off, that's okay. Okay, so if you measure HI, what is it?
John. I got 11.
11?
Full HI.
I get like 9.
9?
Yeah, I
Mine is about 11.
got 7.
7. Okay,
Not drawn.
we'll go with 11.
I
Now,
don't
the
know.
HI is drawn below the principal axis, so it is negative. HO, awesome.
So our grid line is from the arrow to that. And then it should be like kind of close to the HI.
Yes. Yep. The third ray is always a check. First ray, parallel focal. Second ray, focal parallel. Third ray, check your answer. Okay. And then how far is our image from our axis, our device axis? That's going to be our DI. So DI is from here to here.
Oh, I had 31. 37.
37.
37? 37 millimeters. And it is DI positive or negative?
Positive.
Positive, because it's real. In a mirror, the real side and the object are the same. I'm sorry, in a concave mirror, the real and the side has the object and the, anyway, this. Okay, so now we've got a bunch of information, and we can solve. Let's do our math. The math goes like this. Usually we would do our math first, but this is also kind of fun. 1 over F equals 1 over DO plus 1 over DI. You said the focal distance was 22. And by the way, I did this, I made sure I just doubled the C. Sometimes you're given C and not F. Have C and you get F. Sometimes you're given F and not C, double F and you get C. So 1 over 22 is 1 over 55 plus 1 over, where's my TI, 37. And the way I put this in the calculator is I go 1 divided by 55 plus 1 divided by 37, enter reciprocal. Don't forget the reciprocal at the end. Luckily, our graphing calculators know what if you have 2 addeds and then two products, they'll add the products together in their own little parentheses. But go ahead and check. It is 1 over 55 plus 1 over 37 equal to 1 over 22? Approximately.
Pretty close.
Yeah.
Yeah.
Usually we use the art to check the math, but we can also use the math to check the art. So far so good. Now, magnification. Magnification has 2 formulas that should agree. It's HI over HO, and it's also equal negative DI over DO. So see, what's the magnification of this? Do them both ways. It's 3 pages. What's the magnification?
I got 0.69.
Negative 0.69.
Uh,
So the negative tells us that it's an inverted image. The m being less than 1 tells you it's reduced. And now that we're all done, we now label our image with the 3 words. Is this real or virtual?
Real.
It's real. It's on the same side as the light, so it's real. Is it inverted or upright? It's inverted. We know it's inverted. Not only does it look like it's inverted, but our magnification is negative. And then is it reduced or magnified? It's reduced. And we know it's reduced because the m is less than 1. That's how you do ray diagram. 2 rays, parallel, focal parallel, and check.
Anger.
All right. By the way, if you do not have 3 colors and a ruler, you are welcome to borrow them. And staplers are over the microwave. So this is law of reflection, and then these go together. So I don't know why I put it this way. Law of reflection. Okay, that's you can if you don't have a protractor, you can borrow a protractor too. And then on the back side, these are reflections, and these are the math. Now take a look on the 4th reflection down here. This is concave mirror, concave mirror, concave mirror, convex mirror. So on the 4th one, the object is not virtual. Okay? So here, does that, you know understand what I mean by that? So this is the virtual side, this is the virtual side, this is the virtual side, because the object is always, sorry, this is the real side, this is the real side, this is the real side, because the object is always real. But in the 4th one, the object's over here. So this is the real side, making the focal point negative.
We have to do this.
Okay, so the way these work is this is your rough draft, your answers go in the computer. And the autograder will help you fix your answers. That's just practice. Yeah, that's just, if we had lots of time, we could do it, bang a few out. But are you comfortable with ray diagramming, or do you want to do another one together?
Let's like speed run one.
Speed run one? Sounds good. Pick one of the rest of them.
4.
Number 4.
Let's do 4.
All right.
Just like I was not gonna say it with
Wait, you don't get twisted.
So go ahead and start measuring things, and I'm going to start drawing it out.
What do you
Where am I?
So 29.
So she get 54.
Or what do you getting 50 for?
The distance between that and that
Oh, don't we just, that arrow have it on?
Yeah, it's just arrow.
13, that's 29.
Yeah.
What did you get for the distance of the object?
29.
Video is 29.
29. Right. So that's our object right there. D-O. And how tall is our?
13.
It's all 15. Okay. All right. So DO. I already forgot. No DO.
29.
13, 29. Okay. And again, this is a convex mirror. In other words, it's curving this way. So our F is going to be negative and our C is going to be negative.
So negative 21.
That is how much?
Negative 21.
Negative 21. That means our C is negative 22. Yeah, you could be right there. Okay. Did you remember that rays bounce off a mirror? The ray that goes back to the focal distance goes back virtual. Do you see what I did? Parallel. Does your work look like my work?
Yeah, I think so.
Okay, so here's our DI, here's our HI. F. The math should still work. When you put it all in, it's still going to be 1 over F equals 1 over DO plus 1 over DI. Big difference here though, the F is negative. 1 over negative 21. The DO is always positive no matter what. And then you can solve for DI and see if it is where you think it is. All right, how you feeling about this?
It's pretty close.
Any questions?
What's
Okay.
DI?
DI is that distance right there. I found it to be approximately 13. Sorry, negative 13. So I got DI to be negative 13, because again, it's on the virtual side. So since this is the mirror, this is the real side, because that's where the object is, and it's a mirror. This is the virtual side.
How would you draw the third ray on this?
Yeah.
You would start at the object and aim at the center of curvature and just go right through. I don't even bother to draw the third ray, I just use it as a check. I used to always draw the third ray, and I realized it just muddles stuff up. I just use it to check the other two. Okay, last thing, let's go ahead and label this. Real or virtual image?
Virtual,
Virtual image. Is it upright or inverted?
upright,
Upright. And is it magnified or reduced?
Reduce.
Reduced. Again, something that has, so reduced basically means you have a magnification, the absolute value of the magnification is less than 1. Upright means the magnification is positive. And virtual means your DI is negative. All right, I think, and tomorrow it's lenses. Yay, lenses! Okay, so do that worksheet tonight, please, 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 please. That way because lenses kind of throw everything, make everything backwards. A mirror is the opposite of a lens. So lenses are going to get a little funky. Some of the rules are still the same, but not all of them. Questions? Bye, Amy.